You know how to build the linear regression model. Now let's see how to evaluate them. Previously, we saw the measures of goodness of fit. The measures of goodness of fit were R square, adjusted R square, F statistic, AIC and BIC. Using these measures, you can tell how good a model is. But all these measures typically are computed based on the training data itself. The model is evaluated on this data itself. It is also important to validate your model on a data that it has not seen. That is why we created the test data and compute evaluation measures. And those measures were the mean absolute error that we have here, mean absolute percentage error, root mean squared error, and mean squared error. Besides this, you can also use minimax error or min-max error. Let me explain what these are. From this list of 5 different evaluation metrics, the mean absolute percentage error and the min-max error lies between the range of 0 to 1 or 0% to 100%. So this gives an advantage where you can compare the performance of two different models even if the y variable is of different scales. One y variable could be in tens, another could be in thousands, but still you can compare how accurate these two models are. Let's understand each of these measures. Imagine you have built your model already and made your predictions on the test data. So you have the actual values in your test data and you have the predicted values y hat in your test data. Let me create few cases. Let these be the actual values for the sake of computation. And these be the predicted values. Now the error, the raw error can be computed as the difference between the predicted minus the actual. Now the mean absolute error is nothing but you take absolute values of the error. So this would be 2, 8, 2, 2, 4. Sum all of them up and divided by the number of observations. So 18 by 5, and that gives you the mean absolute error. Mean squared error, on the other hand, you compute the square of the errors instead of the absolute values. So that would be 4, 64, 4, 4, 16. Sum all of them up and divide by the total number of observations. So that is 92 divided by 5. That is mean squared error. Root mean squared error is very similar to the mean squared error, only that you take a root after doing mean squared error. This is meant to bring the errors on the same scale of the y variable itself. So this is the original scale. This is squared error. So this will be an inflated value. Taking a root of that will bring it to the original scale. That is root mean squared error. Mean absolute percentage error, on the other hand, is also similar to what we did, only that instead of having an absolute or squared value, we take the percentage error. So the percentage error would be nothing but the error divided by the actual value. Here in this case is 10, and take an absolute of this would give you 1 by 5. Likewise, we do the same operation for all the rows, sum all of them up and divided by the number of observations. Finally, the min-max error. Min-max error is less common actually. The min-max error is nothing but you divide the minimum of y and y hat by the maximum of y and y hat. So that would be the minimum of 8 and 10 would be 8, maximum of 8 and 10 would be 10. Likewise, in this case, minimum is 50, maximum is 54. This ensures that the lower value always go to the numerator. All right. So we have already said the advantage about the MAPE and the min-max error. It always lies between 0 and 1. So that is the advantage. What is the disadvantage? The disadvantage is both MAPE as well as min-max error can give spurious results if your y values are very low and close to 0. Imagine if the actual value of y in some of the observation is 0. In this case, it would lead to a zero division error, and that would in turn cause a very high MAPE or min-max error as well. So you must consciously avoid using these metrics in those cases.